It's a pleasure to be here. So my talk today will be about F-theory GATS and the discrete symmetry extensions. The outline of my talk is the following. I will start just for motivation with a few introductory remarks. Then I will just say a few things about F-theory and elliptic fibration. And thanks to the morning speakers, I will not say much because they have covered all these introductory things. And then I will focus mainly in this part of my talk, which is the discrete symmetries which come together in F-theory with GATS. And if I have time, I will say a few words about Mordell-Weil V1s and GATS symmetries. And I conclude then. Okay, just for motivation, let me start with well-known properties of the old ordinary GATS. And these are the following. There are interesting features in the old GATS, and among them is the gauge coupling unification, of course, the assembling of the standard model fermions in a few representations, like 10 and 5 of SU5, or the 16 of SO10, and charge quantization, as we know. But there are also deficiencies, and among them, the ones that interest us here, is that fermion mass hierarchy and mixing is not explained. And also, the Yukawa-Lagrangian is poorly constrained, and as a result, we have baryon number violation and so on. And the solution to these old GATT theories requires new insights, such as discrete symmetries and Yuan symmetries. And the claim is that F-theory gives this in a natural way. So the new ingredients that I will use from F-theory is that, first of all, we will see that the symmetry predicts in a natural way discrete and Yuan symmetries, which are necessary tools to suppress and eliminate undesired superpotential terms. And also, we will see that we have seen already in the morning that fluxes truncate GATT representations, and in this way, they eliminate color triplets if one chooses in a wise way the flux parameters, and induce chirality in so many things. And finally, the internal geometry of the compact space determines many arbitrary parameters from the standard model and the GATT theories from a handful of topological properties. So more or less, this is the motivation that one works in F-theory model building. So let me just repeat a few of the morning introductory things just for completeness. If one writes down the spectrum of type 2 symmetry, type 2 superstring, then one sees that there is a scalar field, a dilaton, and a scalar potential. And one can combine these two things, these two things in a modulus. So if one writes down an action, one gets the expected equations of motion. The action is SL2Z invariant. And the geometric picture, as we have seen in these morning lectures, is something like this. There is this B3 surface, which is a three-complex dimensional thing. And at each point of this surface, we attach a torus. And the torus has a modulus, which is exactly the one that we described previously. So we live in a space of 12 dimensions, where 8 of them are this Karlab-Yau fourfold. And now this is the fibration that we just described, and it is described properly with the Weierstrass equation, which is given in terms of the x and y and z homogeneous coordinates and f and g functions, which have certain properties. And if one checks the discriminant of this Weierstrass equation, which defines the elliptic fibration of the space that we just discussed, is given by these functions. And then the zeros of this discriminant give the fiber singularities. And if we go back to the previous figure, we see that we have a pinched radius here of the torus. And this red point means that we have the singularity. And it is exactly the point where the 7 branes intersect our surface. So the singularities of the manifold are classified according to Kodaira with respect to these ADE groups. And this classification is based on the properties of the functions f, g, and the discriminant. Now the conjecture is that the interpretation of these singularities is that these geometric singularities are in fact the gauge symmetries that we discussed. So if one wants to build a model, one has to rely on the following kind of groups, either SUN groups or SOM, or the exceptional groups, and the highest singularity is E8 if one checks all these things, and this means that the highest symmetry that we can have is the E8 exceptional symmetry. There is another nice way to describe this in addition to Godaire's classification, and this is Tate's algorithm. One writes again the previous Weierstrass equation in an expanded form in a certain way, and then one has the coefficients alpha 1, alpha 3, and so on, and then the classification of the singularities is given in terms of the vanishing order of these coefficients with respect to the proper variable that we have, and also the vanishing order of the discriminant. So here I just pick up some interesting cases. These are partial results. One can find the results in well-known papers. So for example, if one wants to have the E8 group, then the vanishing order of these coefficients is written here, as we see, and so on. Okay, now, since we have an E8 singularity, which means the maximal thing that we have in our theory is an E8 gauge group, gauge symmetry, suppose that we want to have in our final theory an SU5 or SO10 as a gut symmetry. This means that there is a commutant in our theory, and just after monodromies, this commutant symmetry might be U1 symmetries or some discrete non-abelian or abelian symmetry. Sn, for example, is the permutation group of n objects, An is the even permutations, and so on. So the main idea is that choosing the group, the rest of the symmetry acts in our theory as family symmetry or something like that. In the particular model that I'm going to describe, I will stick to the SU5 case, which means the E8 contains the SU5 and also this perpendicular, as we call it, group. And one can describe the situation by the so-called spectral cover approach. And this means that there is a corresponding polynomial, as you see here, which defines properties around our singularity, around our SU5 group. Just because of the SUN symmetry, I just point out that B1 should be 0, the coefficient I mean here. And I designate for the rest of my talk the roots of this polynomial to be Ti. So the picture that we have, and you have seen also in morning talks, is the following. Here is the gut surface, is a divisor in our internal manifold, and 7 branes just intersect in various ways our surface, and the intersections define the matter curves where the matter resides. And when we have intersections of 3 matter curves, then we have the Yukawa couplings. In the case of the bottom Yukawa coupling, we have an enhancement of the symmetry of SU5 to SO12, and as is well known, for the top Yukawa coupling, we have an enhancement to E6. So this is more or less the picture of our theory. One can also compute Yukawa couplings, and many papers have appeared in this direction. And there is an interesting calculation, and one should also do this thing if one has to compute and see what the model tells us about physics and about low energy and experiment. Okay, now let me focus in the main part, which is the discussion of the non-abelian symmetries, the discrete symmetries that we are interested. What is the motivation for this? Actually, the motivation is the neutrino sector. We know that in the neutrino sector there is large mixing. And this mixing is called tri-bimaximal, and the phenomenology and the experiment have shown that this is very close to this tri-bimaximal mixing, the neutrino, the corresponding neutrino Kobayashi-Maskara matrix. And it was shown by many papers in the previous decades that symmetries like the S4 or A4, these non-abelian discrete symmetries, describe in a very well way manner the mixing effects in the neutrino sector. So because of this, we choose to split the spectral cover to C4 times C1. This means that the defining equation of the spectral cover splits into two polynomials. This is the fourth order polynomial, and this is a monomial. So C1 is associated to a Yuan symmetry, and C4 under monodromies, the symmetry is some Galois group of S4 or some Yuan symmetries or whatever. And how one can define this symmetry? Let me first say that suppose that our symmetry that we have is a subgroup of the Galois of S4. So the Galois group, we call it now H, and the final symmetry of our model is therefore the SU5 times H times the U1 that we've seen before. So this will act as family symmetry and also will eliminate several dangerous terms of the superpotential. This is what we expect. The interesting thing is that this group is linked to the specific topological properties of the coefficients of the polynomial of the spectral cover that we have just shown. And such properties are geometric symmetries, which, as we will see, give R parity, or flux restrictions on the matter curves, and these determine multiplicities and chirality of the model. So in order just to have a picture of these symmetries, I'm showing you this graph. So in this approach that we start with an S4 symmetry, commutation of four objects, and there are various ways just to go down, either through D4, this is the symmetry of the square, or A4, which are the even permutations, or S3, and so on. I will say more in a few minutes. So, okay, how we relate the Galois group with the geometry? The idea is that one has to examine partially symmetric or symmetric functions of the roots, and for our purposes, we need only to examine the discriminant and the resolvent. The discriminant of, in our case, is given, is always given, of course. The discriminant is given through this quantity, which is just the product of differences of roots, and delta square is exactly the discriminant. Note here that delta is invariant under the even permutations of S4, which gives A4. And also, because delta is symmetric with the roots, we know that it can be expressed in terms of these coefficients alpha I of the spectral cover equation. So we have something like this. And now, if, for example, these coefficients belong to some field F, we have the following possibilities. If delta, this quantity here, belongs also to the same field, then we say that delta can be written as a delta square, and in this case we have, as a Galois group, the A4 symmetry or the Klein group. And in the other case, if we cannot do this, then the group that we have in the previous picture that we have seen is S4 or D4. So we add also the information of the resolvent. The resolvent is a cubic polynomial, and it can be written in terms of x1, x2, and x3, and these are combinations of the roots of the spectral cover equation. And as you see, these roots, x1, x2, x2, are invariant under the dihedral group D4, which is the subgroup of S4. So if we combine all this information here, we have this standard table, which is given in standard textbooks, and tells us what the Galois group is with respect to the discriminant properties and to the resolvent. So we will focus here, as I said, in this case, in the corner, which means we will imply this chain down by accepting that the discriminant is not a square of something, and that the function fx, which is the resolvent, is reducible. And what are the conditions that we get under these constraints? The conditions, first of all, is the tracelessness condition, B1 equals 0, and this is solved in this nice way here. And also, because of this chain that we want to go, we have to respect also this constraint. And finally, for the reducibility of the function fx, one possible condition is this one that you see here. Okay, in order to construct a consistent model, one has also to invent a parity, a matter parity or R parity. There is a geometric way to describe this parity, And it was initiated, this idea, in this paper here. And so observe that the spectral cover equation is invariant under these transformations. And if you just focus on the case of the C4, then these equations and these equations here that relate the coefficients of the new polynomials with the C5 spectral cover give also the transformation properties of the A's. But recall now that the A's are involved in the defining equations of the matter curves. And this means that we have a way to communicate this Z2 geometric symmetry to the matter curves. And the only thing one has to do is just to interpret that this is indeed a matter symmetry or a parity symmetry. Okay, under the flux choice that we have done and various flux parameters, one can end up with a table of the matter of the model like this. The model finally is the SU5 times D4 times U1. So you see here we have the 10s and the 5s of the SU5. Here are the defining equations. And here, because of the defining equations, we have the parity that we just described in our last transparency. Here it is the content of the model. It is the standard model plus pairs, which are vector-like pairs, which means that we can also give them masses at a high scale if we choose properly the singlet waves. And finally, we see that we have non-trivial transformation properties under D4 symmetry. And this is exactly what gives us, the structure of the mass matrices in the way that we expect, especially for the neutrino sector. If I focus only on the case of the matter of the standard model, just to make it more clear here and more transparent, I see that I have also here doublets under D4 and various kinds of singlets that appear in this particular group. And here is the Z2 symmetry. I just wanted to tell you that this Z2 symmetry is not exactly the R parity that we know, but as we will see, it is enough just to prevent the dangerous terms of the superpotential. So let me just focus on 2 points of the phenomenology that interests us. The one point is just because of the motivation to use non-abelian symmetries is the neutrino sector. We implement the standard, of course, SO scenario to obtain the light Majorana neutrino matrix, which is relevant to the experiment, and the structure of the matrix looks like this. And the parameters here are just Yukawa couplings, which are supposed to be calculable, and also some vacuum expectation values of singlet fields, which are supposed to be, and are, of course, constrained from DNF flatness conditions. So there are many parameters of the model because of the Yukawa couplings involved, and so we have to just make some plots to see if at least reasonable values of these parameters can give the experimental results that we know. So here the first figure shows us the sine square theta 1, 2 mixing angle theta 1, 2 in the neutrino sector, and the blue line, pink line, and the yellow line are all shown here to define a region in this parameter space x2 and x3, which are some vacuum expectation values divided by some others, so it's just numbers. And for the middle case, we have sine square theta 2, 3, and here are the lines which are drawn with respect to the values, the experimental values that we know. And finally, the third figure here, we see it's this ratio, which is the ratio of the mass square differences of the neutrinos, as you see here. And one can observe that there is an overlapping region of x2 and x3 parameters that satisfy all these experimental constraints. So there is room to accommodate, if you wish, the data of the neutrinos. But the most interesting fact in this kind of models, and I would say the imprint of this model, is the following. We have baryon number violation. Because the symmetry, as I told you, the R symmetry does not eliminate all the R parity violating terms. But there is another good thing here. The good thing is that if you see, the flux can eliminate part of the representations of the SU5. So in the particular model that we discuss here, flux eliminates this component of the 10, which is the quark doublet. So if I write down the only parity violating term of this particular construction, I see that at the standard model level, I have only one term. There is one term missing. If I had the other term, then I would have proton decay. This means that I do not have proton decay, or at least it is suppressed, and it occurs only in higher orders. But on the other hand, I have neutron and antineutron oscillations. This is enough to give me neutron and antineutron oscillations. And this is one graph taken from this paper here, this box graph, which supports this, interaction. And taking into account the recent LHC bounds, one can see that one can calculate the width and then compare with the experimental limit for the time here. And you see that the relevant Yukawa coupling here, lambda b du, is constrained by these curves here for 3 different values consistent with the recent LHC constraints. And here the axis is the squark mass for the top. So somehow calculations in these F-theory constructions give something of the Yukawa coupling, which is 10 to minus 1 or so, which means we are safe somehow, but not far from the future experiments of N-bar oscillations. So more or less, this is what I wanted to say for this model. Let me just focus on a different subject, and this has to do with the Mordell-Weil U1s and the gut symmetries. In the morning, Sakura gave a very nice talk about these things. I will focus only on a very special point, so I don't have to go into many details because it was already explained. The only thing that I want to mention here is that I'm interested in a model which has only one U1. I think the most viable case to have a model is not to have many U1s, but 1 or maybe 2. After that, the game becomes difficult, and possibly you cannot write many superpotential terms sufficient to interpret low energy theory. So we know the following, that there are abelian symmetries which are associated to the rational sections of the elliptic curves, and that there is an abelian group with finite rank, which is of course unknown, but also there is a torsion part in your theory where this torsion part contains discrete symmetries, and these are classified by mathematicians to be Zn, or this product here, as you see. So in principle, if one wants to build a model with these Mordell-Weil U1s through this construction here, then one can also find discrete symmetries that are very useful in the way that we described before. So let me focus now, in this case, for only one U1. It was shown in this paper and many others that followed that in order to describe a U1 Mordell-Weil group, rank 1 group, you have to introduce 3 sections with the weights shown here, and so somehow you are in a weighted projective space of this kind. And it was shown that the equation that describes this situation is the following here. You see here the W, V, and U, and some coefficients that have special properties. Okay, but what is the question now is, what is the non-abelian sector of the theory? I mean, the classification of Kodaira. In order to obtain this classification, one has to do a birational transformation, and one can see that there is a birational map. There are 2 actually, one of these is this one, that gives you the Weierstrass equation. In fact, it gives the Weierstrass equation in the Tate form that we showed in the previous transparencies. But there is something here. If you start from the rational representation of the matter curve, of the equation, of the elliptic equation, then you get the Weierstrass form, or the Tate form, where the coefficients have specific form. They are not completely arbitrary. The idea now is just to compare this specific form of the Weierstrass, of the Tate equation, with the general Tate equation. And there is an observation that these coefficients here are related by this condition. Okay, this gives the idea to go and assume local expansion for the Tate coefficients and see what the implications for the gauge groups are. take, for example, the SU2N groups, and assume now the vanishing order exactly as Tate algorithm tells us, which is written here. And then apply this condition that we got, and this means that n is fixed to 1. This means that we have only SU2. So there is a constraint in the gauge sector of our theory if we have one model value 1. If you do this for SU2n plus 1, then you get only SU3. And if you do this for the exceptional groups, then you get only 6 and 7. Here is the vanishing order of the coefficients of the original equation, which describes the rational sections. So somehow I find that this algebraic exercise is just shows you a simple property which perhaps is suggestive for a model of the type E6 cross U1. But this remains to be seen, and we are working now on the details of such a model. So let me now summarize. I have talked about a model which is based on the SU5 GAT group, and also there is some discrete symmetry and a U1 symmetry, and I have stressed that these symmetries are incorporated in a natural way in our theory when we discuss F-theory models. And the imprint somehow of the model is that we have NN bar oscillations and at the same time suppressed proton decay. On the second part of my talk, I have stressed that when you write down the equation for the rational sections of the elliptic curve, then you get constraints on the non-abelian sector. And in the particular case that I discussed here is that there are two models that come out and they can incorporate the standard model into their structure. So this might be very interesting for future explorations and model building. And there is another nice fact that we also have torsion, and this torsion means that we have discrete symmetries. And in this particular model, for example, one can easily see that there is a Z3 symmetry, although I have not shown this. So more or less, these are the remarks of the models that I discussed. And instead of conclusions, I wanted to show you this picture here where the next meeting is going to happen. Thank you very much.
Thank you very much. Questions or comments, please?
You assumed a three-by-maximal mixing, which was completely okay a few years ago, but now we have the measurement of theta 1,3 from Daya Bay, which is around 13 degree. So it's very, very large, and I think that kills your construction. I mean, your model is excluded, or do you have any idea how to break your discrete symmetry and to include a large value for the reactor angle?
Well, what I was saying, and maybe I didn't say it in the correct way, is that the original motivation was that there are measurements of the angles close to tri-bimaximal. But as you say, it is true, it is not anymore. Yeah. Yes, okay. But the structure of the theory, as I showed to you, is such that allows large deviations of tri-bimaximal mixing. So although the original motivation was the tri-bimaximal mixing, the experimental results that I know, and if these are correct, are in accordance with some part of our parameter space. So if I said that we have tri-bimaximal mixing, you are right, I was not wrong, correct.
Another question about anomalies. So to what extent have you checked the absence of anomalies that typically arise?
Well, in this particular model, I have not checked it, that's true. In similar models in the past, we have checked the anomalies, but in this one, no.
Okay. Other questions? Okay. If not, we thank Josh again.
Thank you.